Hello everyone. In this video I want to talk about a topic which is a separate formulation for equations of motion in a dynamic system. So far you have learned, if you watched my lectures, there are different ways to formulate the equations of motion. The most famous one is the Newton equation, right? Sum of the forces equals the rate of change of momentum, P dot, right? Which, if mass is constant, you can show this is equal to mass times acceleration. Then we had the work energy, which was basically the total work between two positions is the change in kinetic energy. And we had the impulse and momentum, which is the integral of sum of the forces versus time, basically is P2 minus P1, and P here is the linear what? Is the linear momentum, P equals m times v. Okay, so these are the equations that we learned so far. We also had the Lagrangian formulation, which was basically if Lagrangian was defined as the kinetic energy minus the potential energy, K minus V, or you might see I used P in some of my previous formulations, but here I'm reserving P for the momentum. Then the equation of motion in Lagrangian, if you remember, it was d over dt of partial of Lagrangian with respect to q dots, right? Where q here is the generalized velocity minus partial of Lagrangian with respect to the generalized coordinate q. This is equal to the general non-conservative force, okay, which involves external forces as well. So that was the Lagrangian equation, which we also use. And today I want to show you one last formulation called the Hamilton's equation using a new operator called Hamiltonian H, which is closely related to the Lagrangian. So let's take a look at this new notion. So what is Hamiltonian? Hamiltonian is a fundamental concept that you use in classic mechanics as well as quantum mechanics and statistical mechanics. What I'm concerned in the lecture today is only about classic mechanics, which is my area. I'm no expert in quantum mechanics, but in quantum mechanics, the Schrödinger equation, which is the basic equation in quantum mechanics, if you look at the Schrödinger equation, it has this Hamiltonian in it as well. So that's why this Hamiltonian is an important thing. So what is it? It represents the total energy of the system, okay? And you might say, well, when you did introduce the work energy, one of the things you said that you can also rewrite this work energy as the change in kinetic energy plus potential energy was equal to the work of non-conservatives. W. It was equal to the work of non-conservative forces. Are you talking about this guy here that you call the mechanical energy of the system, the total energy? Exactly, that's what we're talking about. This one is also called the Hamiltonian. This H, the total mechanical energy. And you can see that the definition of Hamiltonian is K plus V, or you can call it summation of I from 1 to n of Pi Qi dot minus Li, where Qi is the generalized coordinates, right? And Pi is the generalized momentum or momenta in general, and L is that Lagrangian here. So you see that H and Lagrangian are related, or another way to write it is simply kinetic energy plus potential energy, the total energy of the system. Now, if you introduce Hamiltonian like this, you can show that the equations of motion for the system are going to be these equations, which we call the Hamilton's equations. So they're going to be that the time derivative of Qi dot is partial of H with respect to Pi, and the time derivative of momentum Pi dot is negative partial of H with respect to Qi plus any external force that acts on what? On that ith degree of freedom. Okay, so these are these equations. And to make it more clear, I want to show you a couple of examples so you see how we use these Hamiltonian equations here, or Hamilton's equations. So first, we want to look at the mass spring damper system with an external force, So here we have this mass, and it is driven by the external force, and it is also what connected to the fixed support with a spring K and with a damper C. Okay, and we all know how to find the equation of motion for this system if the motion is shown by x. Okay, but here we're going to derive that using what? Using this Hamiltonian formula. So clearly here your system has only 1 degree of freedom, so n that you see in this summation is simply 1, that's the total degrees of freedom, and your generalized coordinate q is simply x, the motion of the particle, right? So here we have this, that q is x and n is 1, and the momentum p is simply mx dot or mv. Now, if that's the case, Hamiltonian, which is k plus v, is going to be what? Is going to be 1/2 mv squared, which can also be written as v squared mv squared, the whole thing over 2m. That's another way to write it, correct? So another way to write it is to write it as mv squared over 2m, and mv is p, so you can write it as p squared over 2m. That's your kinetic energy, and the potential energy is simply 1/2 k x squared, and x is q, so it's going to be 1/2 k q squared. So this is your what? This is the Hamiltonian for the system, the total energy. Now we say q dot, based on this formula, is partial of h with respect to p. So what is partial of h with respect to p? The only p term is this one, and it's a quadratic, so it's going to be 1 over m times p, which you can see here. So q dot is p over m, and then p dot is negative of partial of h with respect to q plus external force. Now, what's partial of h with respect to q? It's only this guy, so it's going to be simply k times q with a negative sign, so negative kq. And then, what are the forces acting on the system? One of them is the external force. The other one is what? This non-conservative force of Cx dot. Where this F is positive, that force is negative. So here you have to add that. Seems like I have a typo here. That is minus that. And again, for x dot, I'm going to replace it by x dot mx dot over m, right? So it's going to be mx dot over m, and mx dot is p, so it's going to be negative cp over m, which is this guy, and then the external force, of course. And so if that's the case, these are your equations. This is the first equation, q dot equal p over m. The second equation is p dot equals negative k times q minus c times p over m plus f, which is exactly the same as saying x dot equals x dot, which is obvious, right? Because p is mx dot, so divided by m, you get x dot equal x dot, which is obvious. And the second equation is partial the time derivative of mx dot, which is mx double dot or ma, right? Equals what? Negative kq, q is x, negative cp over m is cx dot, and f. And you know, if you rearrange this, you're going to get the familiar equation, which is this guy. And this we had a lot in vibrations, so this is no new thing for this system. Okay, and you might say, well, so what is this first equation doing here? Yeah, you're right. Here, if you look, instead of my governing ODE, which is a second order ODE, which we typically get through Lagrangian or through work energy or through Newton equation, right? If you look at the Hamiltonian, you get what? You get 2 first order ODEs. You see here you had 1 second order ODE. Here you turn it into 2 first order ODEs, and guess what? This is exactly what we did when we wanted to solve this system with, let's say, ODE45. Remember in MATLAB when we used ODE45? We had to break down the system into a bunch of first order ODEs, correct? That's exactly what Hamiltonian does. So Hamiltonian will give you what? The state space representation of the system. Or you can say this P and Q are like those dummy variables that you picked. Okay, so Hamiltonian gives you what? Hamiltonian already gives you the system into first order ODEs. And so it is ready to be used for any numerical solver like ODE45, any other solver, right? And any numerical solution. So it's very good for numerical solutions, this method. And one thing that you have to pay attention is this is all the forces applied to that particle. And clearly you see that C is there and F is there. So this is basically a non-conservative force that is applied to that particle. As another example, you want to look at a 2 DOF system with mass M1 and mass M2 connected by a spring constant K. So here you have a 2 DOF system. This is K, this is M1, this is M2. And of course the system has a degenerate mode, so it can move without any constraint, right? So if you find the natural frequencies here, one of them is going to be 0 because the system can do a pure translation in this case. But the system has 2 DOF and N is 2, so Q1 is clearly X1 and Q2 is X2, and then P1 is X1 dot and P2 is what? X2 dot, and M1 X1 dot and M2 X2 dot because the masses are different. So H, the Hamiltonian, is K plus V. Now K is summation of the two kinetic energies, which is that one. And V here is the potential energy in the spring, which is 1/2 K times the deflection squared. And deflection is the difference between X2 and X1, which is this guy. So that is your what? That is your potential energy. And so if you write the system equations here, in this case on these objects, there is no external force that affects their x1 and x2. There is mg and n, which have no effect on x1 and x2. So that external force term, this guy, is 0 for both of the blocks. And so in this case, q1 dot, because we have to apply for each I now. So q1 dot is partial of h with respect to p1. And partial of h with respect to P1 clearly is what? P1 over M1. Similarly, Q2 dot is partial of h with respect to P2, which is P2 over M2. Then P1 dot is negative partial of h with respect to Q1, and that is only this term. So if you see this negative come out, but there is another negative, so they cancel each other, you get a positive K, Q2 minus Q1, but for P2 dot, negative partial of h with respect to Q2 here, this positive one comes out with that negative sign behind it, you get negative of K, Q2 minus Q1. And if you look at these equations, this is exactly what? This is exactly M1 X1 double dot equals K times X2 minus X1. And here, this is what? This is M2 X2 double dot equals basically negative K x2 minus x1, which are exactly the equations of motion if you use the Newton or any other method, any formulation. We're going to get this, and as I said in this case, one of the degrees of freedom, one of the vibration degrees of freedom is like pure translation, and one of them is basically vibrations, okay, or oscillations. So here you can see that we can get, as you can see here, we got 4 first order ODEs as opposed to what? 2 second order ODEs. We got 4 first order ODEs, okay? Using what? Using this Hamiltonian formulation. So I just wanted you to know about this because this is important. As I said, it's much more important in quantum mechanics, and also you can see it is really good when you want to do a numerical solution or first ODE solvers. This is really directly giving you those state space equations. So hopefully this video was useful to you. I am going to see you in the next lecture. Thank you.